So we just finished talking about points of concurrency. Remember, a point of concurrency is where three or more lines intersect. And we talked about four different points of concurrency. And three of them are very special because they're going to form a straight line always. And that special line is called Euler's line. I know it looks like it says Euler's line, but it's pronounced Euler's line. So those points of concurrency we talked about were the circumcenter, the centroid, the incenter, and the orthocenter. If you can title your next page in your notes Euler's line and then grab the little one-pager handout, we're going to take some really quick notes on this. So Leonhard Euler, he's this like really famous mathematician, astronomer. He was like really famous, and he created a lot of stuff in math in the 1700s. He's responsible, I think, for giving pi its name using the Greek symbol pi. He, if you've ever done logarithms, which you should have in Algebra 2, he is, the lowercase e is named after him for natural log. He's the little lowercase e. He did, I think he denoted, he gave like the square root of -1. He like, hey, let's represent that with a little italic lowercase I. Anyway, he's done a lot of stuff. He's kind of a big deal, okay? So this is him, and he's got this special line. He realized, hey, there's these special points of concurrency. And if you have the centroid, the circumcenter, and the orthocenter, they always form a straight line. Sorry, incenter. Y'all, you're not part of the gang. So it's always going to form a straight line in a triangle. As long as they're the centroid, the circumcenter, and the orthocenter of one triangle, of a single triangle. Not like three different triangles, but it's got to be the same triangle. So here's an example. It's really blurry because I blew up a textbook picture, but that is the red line is Euler's line. So let's talk about how we find this. So first off, what you're going to do is you are going to actually have to find these 3 points. So you need 2 clean points. Sometimes they're not all clean. And remember, we have 4 points of concurrency. Which one do we not use for Euler's line? The incenter. Okay, so we don't care about the incenter, so don't even waste your time finding it. I mean, we care about it if we want to be equally distant to the sides of the triangle, but not for writing Euler's line. So the centroid, in case you don't remember, the centroid is made up of medians, and a median is when you find the midpoint and you connect it to the opposite angle. Okay, there you go. So I'm going to find the midpoint of these sides. Make sure you use your midpoint formula because this is on a graph, and that's the rule. Show your work. So my midpoint formula, I'm just going to estimate where they are right now. Imagine I did the midpoint formula 3 times. These are the midpoints. And again, to make the centroid, we need to draw medians. So I'm going to connect my midpoint to my opposite angle. So connect, connect, connect. Okay, this is not a pretty long intersection because it's not like at the crosshairs. So let me use technology really quick. And this intersection is 0, 0.67. Coincidence. So I would not say that is the prettiest intersection, but I'm going to write it down because who knows, maybe they're all not pretty because I just made up numbers. But let's find the circumcenter now. So if you can't remember how to find the circumcenter, it is made up of perpendicular bisectors. So you're supposed to find the midpoint, the bisector point, and then draw that 90-degree angle. Use the opposite reciprocal to find the slope, blah, 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 blah. So let's imagine I use the midpoint formula 3 times. 1, 2, 3. Those are my midpoints. And then I found the slopes of each side, found the perpendicular slopes, and applied them to the midpoint. So that is a 90-degree line with everything. So my circumcenter is right here. And also, I guess this is a right triangle that I made up randomly, but the circumcenter on a right triangle is always in the middle of the hypotenuse. Fun fact, only for right triangle. Okay, so that is the point, negative 1, 1. That is a pretty point. So I'm going to write that down. And then let's see, hopefully the orthocenter is easy too, because I would not want to write an equation between those 2 points. That's a lot of work. So the orthocenter is made up of altitudes. We just talked about that last class. And the way you find the altitudes is you find the base, and then you draw from the tippity top point, you draw that perpendicular slope from the opposite side. You find the slope of the side, find the perpendicular slope, and apply it to the opposite angle. And you do that 3 times. So these are my altitudes, and they meet up right here at point C, which is 2, 0. So again, this is a right triangle, so the fun fact about right triangles is that the orthocenter is always on the right angle of a right triangle. But make sure you're showing your work. So those are actually 2 pretty points. So I'm going to use these 2 points to write the equation of the line. In case you don't remember how to write an equation of the line, if you have 2 points, you're going to start off by finding the slope using the slope formula. So I could use rise over run, but I don't have these 2 points on the same graph right now. So I'm going to use y2 minus y1 over x2 minus x1. So my 2 y values are 1 and 0. My 2 x values are negative 1 and 2. So when you plug it in, make sure that you plug it in correctly and that you simplify your fraction. So I have negative 1/3 is my slope of my line. And I don't need to find the perpendicular slope because I'm just finding the equation of Euler's line, which is the equation of the line that goes through these 3 points. So how do you write an equation? Well, there's 2 ways. You learned it back in Algebra 1. You learned point slope formula and slope intercept formula in order to write the equation of the line. Both are totally fine. Whichever way you prefer, just show your work. So I'm going to plug, this is my M, and then it doesn't matter which one you want, but one of them is your x1, y1, or here, in this case, it would be your x and your y. So let me scoot it up. So I'm going to plug in negative 1/3, and I'm also going to plug in the first point. You could have plugged in the second point. It might have been easier. But I'm going to plug in, this is negative 1 is my x1, and y1 is 1. So I'm going to distribute the negative 1/3 through, and I get y minus 1 equals negative 1/3 x minus 1/3, because remember, a negative and a negative make a positive. Distribute a negative through, that becomes a negative again. Get the negative 1 to the other side by adding it, and I get y equals negative 1/3 x plus 2/3. Let me show you the way that I think we might have done it in class this year. Y equals mx plus b. Plug in your slope, and then pick a point to plug in. It doesn't matter which one. I'm going to plug in this for my x value, this for my y value, 1 for my y value. And then I'm going to solve for my b, my y-intercept. So when I multiply those, I get a positive 1/3. When I subtract it, I get 2/3. So my equation of my line is y equals my slope, negative 1/3 x, plus my y-intercept 2/3. And they're the same equation. So you decide which way you prefer better. Let's do another example. Oh, sorry. You could also graph this on the line, and you'll see that it'll go through those 3 points. Let's do another example. So let's see. This is a right triangle, so I could speed through these. But remember, the point of concurrency, I don't care about the incenter, so let's look for these points of concurrency. The centroid is made up of midpoints to the opposite angle. So this is my centroid right here at negative 2, 1. That is a pretty point. And then recall that my circumcenter is always the middle of the hypotenuse on a right triangle, and my orthocenter is always the right angle on a right triangle. So you should be able to identify where these points are on a right triangle relatively fast, probably faster than all the other ones, which is why I'm going to give you right triangles to help you double check your answers, and it'll be pretty obvious. So I have a lot of really good points. I'm probably going to pick the orthocenter and the centroid because they are whole numbers, and the circumcenter is the point negative 1 comma 0.5. But that would get me this same equation if I picked any two. So those are my 3 points of concurrency. It doesn't matter which two you pick. But let's start off by finding the slope y2 minus y1 over x2 minus x1. Oh, apparently when I did these, I used the ugly point. So I used 0.5 minus 1. Oh, I just used my first 2 points. Over -1 minus -2. So x2 minus x1. And that simplifies down to -1/2. Or -0.5, which is -1/2. I like to write my slopes as fractions because I think of them as rise over run, but you can totally leave it as a decimal if you want. Okay, then we want to write the equation of the line. Again, your choice how you do it. I'm going to use point slope form today because I have a slope and I have a point. So this is my x1, this is my y1. Don't get them flipped because y1's on the left side, right? So make sure you put the 1 here. This is my slope. So when I plug everything in, it looks like this. A double negative makes a positive, and then when I distribute, yes, it would make it negative again. So I get -1/2 x minus 1/2 times 2 is 1. And then I'm going to add 1 to both sides, so I get y equals -1/2 x plus 0, which is just -1/2 x. And if you look at the picture, let's see, where's my picture? If you look at the picture, this is the red line. See how it has a y-intercept of 0, has a negative slope of rise 1, run 2, rise 1, run 2. I can count using my scales. So that makes sense checking the picture. Just make sure that you show your work. Okay, so tape this in your notes and then work on the worksheet.